I was able to get a little bit from Jenna. So here, the guy that is about to speak graduated #1 in his University of Vermont class in math. He then went to GE and worked at IBM as well. At IBM, as I understand it, he was doing something like visual reading a robot. I guess you could look at self-driving cars being a reading robot. We've got some noise here. Maybe if people can mute themselves. And then at GE, they liked him well enough to pay for his master's degree. He's worked as an independent consultant at Pacific Scientific. The kind of problems it works at is like if North Korea shoots an arrow at us, we shoot another arrow to intercept it in the air. A really easy job. And so
we do a little tiny piece of that.
Pardon?
We do a little tiny piece of that.
Yeah, but the point is that he deals with these. This is not like F equals MA kind of engineering. This is very complicated, multi-dimensional, non-linear kind of experience. So he's a really sharp guy, and I'm looking forward to this. And maybe in future, if we ever meet again, maybe we can actually get him to talk more about himself. So, so we'll take it from there. Mark, take it away.
I don't love people who talk about themselves a whole lot. So anyway, all right. I'm going to try to share my screen, and we can get started. Let's see there. Share. There it is. Go to slideshow. All right. Let's see. All right. Yeah, I want to talk about what I've learned about what's going on with electric cars. Maybe you've seen a few of them around. During the talk, I would like to try, at least in the beginning, to take questions as they arise, because there's some technical content to some of these and some things to unpack on some of these slides. So if you have questions, I'd like to try to deal with them as they come up. If it gets to be too much, then we'll try something different. Another thing too is that each slide has a number in the lower right corner. If you'd like to delay your question till the end, it might be helpful if it's on a particular slide. Remember that number so I could go back to it easily. But this is a picture of my beautiful wife's car, and so she was the brave one and went out and did this novel thing and bought an electric car, and I was so interested in it afterwards. I've spent a lot of time just learning about them. So off we go. One of the things that's happening is that the sale of electric cars is increasing at a tremendous rate, and since say 2015, it's been growing at a faster than exponential rate. And we want to try to sort of get at what's going on there, why that's happening. Also, another thing that we saw in the United States is that we have a number of fairly fancy cars in about the same price range as the Tesla Model 3, but after the Model 3 was introduced, it's outsold them cumulatively, maybe even the top 3 of them it's outsold altogether. And so there's something about this that's really grabbing a lot of attention and getting a lot of sales, and Tesla in particular is basically selling as many of them as they can make. If you look at some of the reasons for that, one of them is that a lot of countries are planning to phase out internal combustion vehicles. This is a chart I got from Wikipedia, and it lists all the countries that are either going to institute strong incentives to stop buying new internal combustion engine cars, or outlaw them, ban the sales of internal combustion engines in all cars sometime in the future. So on the left, we have the countries, and then the dates are in the next column. And so I don't want to go into all the details, but there are countries now where most of the cars, like Netherlands and some of the other countries in Northern Europe, are having more sales of electric cars than any others. And California is also planning to phase out. I didn't list the states, but California is planning to phase out the sales of new internal combustion engine cars. I think 2030 or 35, something like that. So the question arises: why electric cars? This is something I picked up on the web. Most of what I'm going to be presenting is derivative from somebody else's work. But what they have across the top of this chart is starting from, basically they're starting from 100% renewable electricity to make, well, to charge batteries in one case, to make hydrogen for a fuel cell vehicle in the second column, and then for liquid fuels for a conventional internal combustion engine. And at the bottom, you get the overall efficiency. So with direct charging, you have from renewable electricity, you have a 5% transport, transmission and distribution loss. And then you have at the bottom listed all the losses in the car itself, and you end up with 73% of the energy that's produced electrically, renewably, hopefully, is available to propel the car. In the case of the hydrogen fuel cell, starting from the same renewable electricity, 22% of the energy that's produced by the renewable electrical generation is available to propel the car. And then in the case of the conventional internal combustion engine, you have just 13%. And I added some numbers here next to the direct charging column and to the power to liquid fuels in order to remind me of my calculations of what happens if you start with fuel instead of renewable electricity. And in the case of direct charging, if you're using natural gas, and the most efficient generation from natural gas would be a combined cycle gas, which starts with a gas turbine, and which drives the generator. And then the hot gas, that's exhaust gas from the turbine, is used to boil water, and that operates a steam turbine. And that has a 62% maximum efficiency, and then you still have your 5% losses. So this 59% number here represents the electricity that arrives at your house or your charging station. And then the losses in the car itself bring it down to 45%. So if you're burning fuel, in this case natural gas, you get a 45% overall efficiency from the heat produced in the gas to what you're able to use to propel your car. In the case of the liquid fuel car with the internal combustion engine, based on their numbers, with a 70% energy loss in the car, you end up with 30% of the energy that's produced by burning the fuel ends up available for propelling the car. One of the things it doesn't take into account is something I'm going to talk about in the next few slides, which is regenerative braking. A lot of what you can return energy to the battery when you're going downhill or slowing down an electric car, and that's something that's available in a hybrid to a lesser degree, but not available at all in just a conventional internal combustion engine car. So if you're concerned about reducing the carbon emissions or reducing the cost of energy, then the electric car, as far as the technologies we have available now, is the most efficient way to continue operating cars that's available.
Mark, one question on that. The last one where you go from electricity to liquid. What kind of process are you talking about here?
Well, I don't know exactly what the process is. I think probably it may be an electrolysis if you look at the hydrogen fuel cell on to the left of that, you're talking about 30% energy losses. So that's probably going to hydrogen, and then you could react that hydrogen with some kind of a carbon compound, or hydrogenate some oil. So it looks like, yeah, you would be reacting that. Say you reacted with carbon, that 37% energy loss would be. You'd react that, and you'd lose heat in the process of reacting the hydrogen with carbon, and then you'd have some kind of a hydrocarbon chain that would be in a liquid form if you get the right molecular weights.
Okay.
That I'm speculating, but that looks like what they're proposing. I don't know the details.
Jack had a question.
Yeah,
Okay.
I got a little lost at where if the electricity, you were assuming electricity for, let's say, the direct charging might be by gas, natural gas electricity production. Is there, suppose it were by solar, is that anywhere shown here? I didn't quite follow.
By solar is the way they originally did the chart. So that gives you the 73% number at the bottom of the first column.
Maybe another question.
I was just adding, okay, another thought is if you're burning fuel to do it, what do you end up with? And that's the stray numbers that I put in between the columns here. You got to the 45%. But if you're doing direct charging, that's what the original column is about, is from renewable energy to electric propulsion of a car. That's at 73% overall efficiency from production to operating the car, or propelling the car. So that was the original one.
A question about, so if I read the far column right, it says that internal combustion engines are only 30% efficient.
Well, you need to have an average.
Yeah, okay.
About right.
The peak efficiency of a really great diesel or the newest Priuses is likely about 40%.
Right.
But a lot of the time you're operating them at light load. And a lot of what you're doing when you're operating an internal combustion at light load is just pumping air and fuel through it and throttling it so that it doesn't produce as much power as it could. So a lot of that is you end up with a lot of pumping losses, and the average efficiency that you operate at is below the maximum efficiency of the engine.
And then one other related question. There's been these complaints that the production of batteries is the world's worst thing for the environment, et cetera, et cetera. Did anybody, yeah, I'm not buying that, but I mean, there are some issues with it. Did you come across anybody who compared the cost of basically building a battery plant that lasts 10 years versus building a combustion engine that lasts maybe 20 years?
Why would you suppose that the battery plant would last 10 years?
I don't suppose that, but there are people that are probably funded by Exxon that
right.
talk about the pollution, the rare earths, the how it's a non-renewable source. Basically they say batteries are evil. As far as I can tell, the batteries are a better bet than internal combustion engines. If you do a life cycle, costing of the footprint. I'm just wondering if you actually found anybody who did that life cycle costing of, okay, we're going to build an internal combustion engine, we're going to build a battery, and 20 years later, all things considered, what do the two compare like?
Yeah, and I've seen some of those. I didn't bring any of that to this presentation, but if you take an average driver who does maybe 12 or 15,000 miles a year, they say that the extra energy that's put into an electric car now in its production, you get a break even at about a year into operating it. They do also, there are plans afoot to recycle almost all of the materials that go into a lithium-ion batteries. It's basically elements, and you have to separate them out. But what happens is you get dendrite growth and things like that. But the elements are all still available for reuse in new batteries. And when you're done with an electric car and the battery is no longer giving you the range that you want, you can still use them for stationary applications for quite a long time. So you could use them for energy storage in a home or in utility scale energy storage, which is happening at a fairly large scale now.
Thanks.
Okay, the electric vehicles and hybrids can do something that conventional cars can't, which is called regenerative braking. And when you're braking, you're taking kinetic or potential energy and converting it into another form. If you downshift in your car and you're just letting the engine hold you back, you're basically taking in air at a cool temperature and a low pressure, and you're heating it up and pumping it out into the atmosphere at atmospheric pressure, or actually above where it leaves your engine. So what you're doing to take the energy that you get from going downhill or coming to a stop from speed is to heat air in your engine. And if you're using your friction brakes, your disc brakes or your drum brakes on your car, you're basically heating up the disc or the drums and the pads, and that goes into the air. So again, you're just heating air. But the regenerative braking actually uses the electric motors as generators and recharge the batteries. And it's gotten to be a very powerful thing in some of the cars that are pure electric, because you can drive over Highway 17 if you're not driving too aggressively and you don't run into stopped traffic on a blind corner. You can go all the way over on down the other side and never touch your brake pedal. And all of the braking that you do going down that hill, it goes back into your battery. So when I had my first Prius, it got a little bit of regenerative braking. It's a blended brake where you step on the brake, and the first thing it does is it starts applying regenerative braking and puts energy back into the battery. And as if you brake harder, it goes into friction braking. In that car, I replaced the brake pads at 208,000 miles the first time. So it really saves brake wear, and it also saves energy. In the Tesla, you can do as much as 0.3 Gs, 0.3 of a G of deceleration without touching the brake at all. You just let off the accelerator pedal. And so you get essentially the same economy going over Highway 17 as you do the same distance going flat. It's almost not noticeable, the extra energy it takes to go over a mountain. One of the complaints about electric cars is that people suppose that they would just transfer the pollution from where the car is operating to where the power is generated. But as you clean up the grid, as the grid becomes less and less polluting, the power generation grid, all of the electric cars become less polluting as well. And California is admittedly ahead of a lot of other states in terms of renewable energy, but this is a California Energy Commission graph that shows the renewable percentage of the power that's used in California as a function of time. And so it's gone from 22% in 13 to 36% in 2019, and it appears to be continuing to go up. This is a graph that's related to the first one, and that's what percentage of California power generation is solar. So we've gotten up to 26.4%. It looks like it's slowing down a little bit, and I think probably for this to continue to increase, we're going to have to deploy some storage, because of course the intermittency and the timing mismatch between production and demand. But they're building some very large batteries now, and there are other storage schemes like pumped hydro and compressed air that are starting to be built that will allow us to have longer times of energy storage, so that it doesn't really matter very much when power is produced and consumed, as long as it's within a few days of each other. Taking into account more than just renewables, but when you include hydroelectric and nuclear, 63% in 2019 of California's electricity was produced by non-carbon emitting sources. So the impact on carbon emissions from using an electric car is very substantial, because of the efficiency effect in the first case, but also in the fact that the electricity produced is produced almost, well, about 5/8 is produced without emitting carbon. Another thing about electric cars is that they're much simpler than internal combustion cars. If you take an electric motor, the electric motors they use now have basically one moving part plus some gears that also move. But and this is from the paragraph in the Tesla owner's manual. It talks about what the routine maintenance is, and there's no spark plugs to be changed. There's no oil changes. There's no oil filter changes. You're looking at brake fluid being checked every couple of years. Air conditioning desiccant bag every 6 years. Cabin air filter every couple of years. You want to rotate your tires. If they use salt on the roads, you want to check your brake calipers every year. There's tire rotation and your windshield washer fluid, and change the blades once in a while. One of the reasons why conventional auto dealerships don't have much interest in selling electric cars is because their business model depends on regular spending on maintenance, and it's greatly diminished in an electric car. This is from PG&E, and they have an EV plan, and you can do it one of two ways. You can put your house on the EV time of use plan, or you can buy a separate meter and only put your car charging on that EV plan. But the rates off peak are little under 14 cents a kilowatt hour. And if you take a quarter of or about 4, what we get is approximately 4 miles per kilowatt hour. And you charge, it's between, the lowest rate is between 11 o'clock at night and 7 in the morning. So you've got 8 hours. And with a type 2 charger, you can add on about 240 miles of range overnight on the Tesla Model 3. And it comes out to about 3.5 cents per mile of power, of energy use. And so that is less than half of the energy cost for a Prius. So it's extremely cheap to buy the energy for an electric car. If you get the cheapest, and even if you go to a supercharger, which is a fast DC charger that there's several stations around, and I'll show later where some of them are. And there are other charging networks as well. You're looking at, say,
all I care is
26 cents per kilowatt hour, almost twice as much.
We saw the table, but we weren't
Okay.
able to.
Who's talking could
Yeah.
please
Okay, we'll
mute
just-
themselves. So even this turns out to be around 6 cents, maybe no, 7 cents a mile, which is still comparable or slightly cheaper than driving a Prius for energy use. On the other hand, there's a few factors that argue against the purchase of an electric car. One of them is that the purchase price is higher than an equivalent internal combustion engine car. You can't buy a nice electric car for $25,000 yet. Batteries are still quite expensive, and they contribute maybe 40% of the cost of the car. Manufacturers are still learning. They're not very far down the learning curve. There have been vastly fewer electric cars made, modern electric cars made than internal combustion cars, so that the manufacturing technology is still being improved, but has a long way to go. Production volumes are still quite a bit lower, much lower than for internal combustion cars. But I'll talk about this later. Purchase price parity, basically where you can buy an electric car at the same price as an equivalent internal combustion car, is expected by a lot of analysts before 2025, and I'll talk about why that is likely a little bit later. The energy used in production is high. It's higher than it is in an internal combustion car. The batteries do take a fair amount of energy to produce. And so it takes a while, maybe a year, depending on how much you drive, to get to break even in terms of the energy, total energy used by the car. A lot of people still think that electric cars are like $100,000 cars, but they no longer are. In this graph, the first column after the name of the car is the purchase price, and then the next column is the cost of the car, the price, the purchase of the car per mile of range. So if you have a car that costs $30,000 and can go 300 miles on a single charge, that number would be like 100. And so 2022 Chevy Bolt is about $32,000 base price. Long range Model 3 2021 Tesla is about $47,000. And as it goes down the column, they get more expensive. But you can certainly buy a functional car that's reasonable to use for in the 30s or maybe in the high 20s now, and so they're not like the original Model S or Model X where you started about $70,000 or $80,000. And here's why we expect that they're going to become
I've lost the
competitive.
price per mile. Very last column, like
Let's go back.
124 or something.
Yeah, that's
that-
okay. If you
The top line is Chevrolet Bolt 124, then 124.
yeah, but that's because there's no tax credit anymore. The cars that do have a tax credit, those two different numbers are different. So if you look, I think the first one, let's see, that's 145. Okay, the Hyundai Kona Electric, right? If the green is after the tax credit and stuff, and the white, the last column is the price, not including the tax credit. So Chevrolet and Tesla have used up all their tax credits that after the 200,000 have been sold, they start phasing out the tax credit, and every 6 months it dropped in half, and then it goes away. So Tesla and Chevy have used all of the tax credits available, and so those prices will be the same in the last two columns. And then in the, but when you get to the Hyundai, they haven't used up their tax credits in the U.S. And so there's a big difference between the cost after.
I'm sorry, but I don't see price per mile.
I'm sorry?
I missed something.
Well, this is price per mile of range.
$124 on it.
Right. If you take that $124 and you divide it into the 31,995, you get the number of miles that the car will go on a single charge. It's a funny metric, but
Okay.
But it tells you, if you want a car that can go 300 miles on a single charge, in order to get the range of the car from this graph, you have to divide the last column into the price of the car. But I just wanted to illustrate what the range of prices for the most efficient electric cars was. And this was a handy graph to do it.
So Mark, I assume basically you're buying a bigger and bigger battery to get range.
Thank you.
Right. So if you look at the Tesla Model 3 long range, it has about, I think the 2021 is like 352 miles. The Chevy Bolt, the one above it is about 250 miles range. So it's much cheaper. And so, yeah, the cost of the battery is driving the price of these things. And this is the battery cost trend, according to Bloomberg. And over these 10 years, it's dropped by 87%. And that's an average rate of decrease of about 20% per year. If this trend continues out to 2025, the price of the battery packs will be about 40% of what it is now.
Is that, have we come to the end of mass-produced batteries, so efficiency? Because it seems like it's leveling off as it's going.
Well, it's because they're smaller and smaller. It's a smaller step at the same percentage.
Okay,
No, it's not perfectly even, but
okay.
but if you continue that 20% per year trend down to out to 2025, we're looking at something a little over 40% of the current cost, and it starts to be a much smaller portion of the cost of the car. And the expectation is that when you achieve that, we're going to have cars, electric cars, that will have a purchase price that's equivalent to a car of similar capabilities and capacity. It's a internal combustion, along with, you know, giving the same purchase price, but much cheaper to buy energy for and much cheaper to maintain. At which time it's likely that a lot of people are going to opt for this more economical choice. We have a lot of studies, and I haven't brought any of them to this presentation, that are saying that the cost of ownership over 5 years of a, say, a Tesla Model 3 is lower than for, say, a Toyota Camry for an average driver. That may be controversial, but if somebody can make the case and it's plausible, you know, we're getting to the point where it's likely that they're going to be cheaper to own and operate in the near future than an internal combustion car.
Rusty has a question.
Mark,
Okay.
does this mean that people are going to be buying more cars?
Well, actually, people have been buying less cars over the last few years, and I'm not sure why. There's some people who theorize that it may be because they want to wait for electric cars to get cheap enough so that they can afford to buy them, and so they're hanging on to. And there are a lot of young people who are deciding just not to drive.
So a question on the battery prices. If there's both a connection and a disconnection between battery storage for solar and cars, and I'm wondering if you maybe could shed some light on it. We put solar in last year, and we tried to get 2 Tesla Powerwalls, which is basically the same battery technology as in the cars. It comes off the same fundamental production.
Yep.
The Powerwalls were delayed. We learned in January that they may be infinitely delayed, that they're not supplying them, that they're going into cars. And if you put batteries for your house, we're still with installation cost stuff, still close to that $1,000 a kilowatt price. It's about 800 something like that. So what I'm wondering is that because the solar people are screwing us and Tesla can't keep up with demand, or if there's something else going on that I could understand to get batteries to back up our power?
Well, Tesla has stated that for its semi truck that they've had under development, that if they don't have enough battery cells to ramp up the production of that, they're building factories in Texas and in Germany, and they're projecting that they're going to sell about 60% more cars this year than last year. They're building these mega packs for utility scale storage. So they're pushing on the supply constraints for batteries on several fronts. And then there are other companies that are starting to make electric cars in reasonable quantities. They've got some competition in China that looks pretty.
So do you think this is it looks like to me that the 2020 estimate is going to be maybe wrong. And is it a minor blip, or is there anything in the supply chain in terms of a rare earth or lithium supplies or something like that is going to make that more than a blip for a year or two?
I think that it's not going to remain constrained as it is right now. I think that the growth is so rapid that they're not keeping up, and also Tesla is planning to change the
question was-
technology.
Have you considered nickel iron batteries? They, of course, they're too heavy for cars, but wouldn't they be cheaper than anything for, storage such as Peter was asking?
There are other battery technologies that might be better for stationary storage. And there's a tremendous amount of R&D going on in developing battery chemistries and form factors and things, because we essentially have an exponentially growing market for these things, and there are lots of constraints. One of them is that people don't want to use cobalt because, and which they use in the cathodes. I think it's cathodes, and because of the abusive practices in the Congo, where a lot of cobalt is mined, and they're trying to eliminate it completely. And Tesla is using some nickel iron sulfate batteries. I think that's what it is. In China, they don't have quite as long a life. They're probing on a whole bunch of fronts in terms of how to improve the chemistry and form factors of these batteries. And I think whatever they're able to do to improve it is going to happen. It's just going to take a little time.
Thanks.
Probably shouldn't have put this in, but I thought I would. Experience curve, Wright's law. This guy, Theodore Paul Wright at Curtiss Wright Aircraft, I think it was during World War II, figured out that there was an empirical trend in production cost, where the cost of a unit of production at the one, when you have n of them, is equal to the cost of the first unit, or times n to a negative exponent. So we're seeing a continuing cost decrease in the production of these batteries. And I did some additional math where it shows that if you have, if the number that you're producing per year is increasing exponentially, then you'll have an exponential decrease in the cost, according to this curve. So we're, I think that's what we're looking at, is that we have cars have become by far the largest and buyer of lithium-ion batteries, and the number of them is growing at an exponential rate, and that's now what's driving that cost curve down. Another trend in lithium-ion batteries is they're getting lighter and smaller over the years, not as dramatically as the price is coming down, but still the energy density is increasing so that they can get as much energy stored in a smaller battery over time. There's a matter of concern about battery longevity. How long does a battery last?
Yes, but
And
it's fairly cheap.
because they're so expensive, if you have to replace it, how long is it going to last? And there has been a big issue with Nissan Leafs, because they have air-cooled batteries, and they don't strongly control the temperature of the battery. So if you don't pay attention and keep the battery temperature below a certain level, they have a relatively rapid decline in charge capacity. And what Tesla has done, and others have done as well, is to use liquid cooling and to reduce power if the battery temperature starts to climb too high. So if you take a current Model S or an older Model S out on a racetrack and you start driving all out, you might get a couple of laps out of it before it starts to limit the power. they've improved the Model 3 and Model Y batteries so that they have much better cooling, and you can probably go 10 laps all out on within a second or something like that if you wanted to before it starts to limit power. But they grow to great lengths to keep that battery temperature low, and they'll even, I believe they even use the air conditioning system to chill the coolant if they need to, which greatly reduces the range in very hot weather, but keeps your battery from being wrecked by overheating. And
Mark?
yeah,
Mark, I have a question. What is my Model 3 doing when I say I want to go to a supercharger and it says it's preparing the battery? What is it doing?
it's got an optimal temperature for charging, and so what it'll do is preheat the battery to that optimal temperature. If you programmed it, say, to navigate to that supercharger, it'll prepare it by getting the temperature up to the optimum for fast charging.
Okay.
This graph is comes from the experience. There's a club in the Netherlands that has kept track of their charge capacity in Model S and X Teslas over a long period of time. And so they've looked at capacity loss, and it turns out to be about 10% in 170,000 miles. So if you have a 300-mile range in the beginning, at 170,000 miles on average, you would have a range of about 270 miles after you've driven at 170,000 miles. To get to 80% of your original charge capacity, it's typically about 1,500 charge-discharge cycles. So for a car with a 300-mile range in the beginning, you would get to that point at about 450,000 miles after you've driven at 450,000 miles. If you have a 250-mile range, it would be 300-some thousand miles before you'd get down to 80% of the original capacity. It may be better in the Model 3 and Y because of the improved cooling, but we don't have that data, so they haven't been out long enough. In the US, electric cars are mostly Teslas. And I think the reason for that is that that's their mission. They've gone all out to make electric cars. They really don't make any other kind of cars. They don't go through dealers, so they don't have the dealer resistance. And they had a plan to start with a Roadster, which they sold at a very high price. And then after they've made some money with that, they started making the Model S, which was still an expensive premium car, but it allowed them to make enough money to invest in the plant and equipment to start making the Model 3, that and the Model X. And then they basically bet the company on the Model 3. And now that they've gotten the Model 3 to be profitable, they brought the Model Y onto market, and it actually in the US is outselling the Model 3 now. But they've been profitable for 5 or 6 quarters now. No one else has devoted their whole mission to being an electric car company, and they still outperform almost everything else in the same price range. So,
I have a question.
Okay.
I don't own one, but I have a property that my renter has a Tesla, the Model C. And I've been surprised, we're on the same PG&E thing. I've been surprised and he's not going anywhere. He's home working, right? He may go get the mail and get groceries, but he doesn't drive it very much. But he still seems to have to charge it a lot. And how long does it hold a charge if you're not doing anything? Or very little?
It holds a charge for quite a long time, but it will lose a couple of miles a day, you know, some fraction of a kilowatt hour. But why do you think he charges it a lot?
Because I look at my PG&E usage. I mean, he's paying me for it, but I still see it. It's dramatically different than before that car was there.
Oh, okay.
I mean, it's up, and we also don't have the EV thing that you're talking about. But I just looked at that, and in order to get the best EV rate thing from PG&E, you have to put in a separate meter, which has got to cost you something.
Well, you can actually, it has two plans, and you can do one where you are on a time of use plan that's the same as the EV plan, where you have the same meter. At least you could when I checked, which was a few months ago.
Sounds like they do some kind of blended thing, but it's the best rate you were talking about is if you put in your own, a separate PG&E meter, which has to cost a bit too.
Well, but you don't have to do that. But the thing is, you only get the lowest rate between 11 at night and 7 in the morning.
Right.
And it's higher rates at different times. And they may have changed it since then, but you don't actually have to put in the meter, or you didn't at the time that I last
No, I don't
looked.
think you have to, but I'm just not sure what the rates really are. But
Yeah.
anyway,
Well,
so it should hold a charge if
Oh, it
they're not
does.
going anywhere for a couple of weeks, right?
Yeah, it does. It'll hold the charge for a lot longer than that.
It's interesting.
But it does slowly bleed off.
I have a comment on that. We had a home charger with our Tesla, and we originally had it set up for EV charging because we had an EV, and we said, "Oh, that must be the best deal." It's not necessarily the best deal. And when I found PG&E to be very cooperative, and when you call them up, they look at your usage and your time of usage, and the amount of usage over time. And they will come back and say, if you keep using energy at this rate over these hours, during these hours, this is the best plan for you. It may not be the one that you're looking at. So you might call PG&E.
Okay.
Yeah, you
That was
can
my
also,
experience as well. Worked out very easily.
you could also talk to your tenant and you know, you have a timer in the car that
Oh, that's how he has it set up. He's only doing it at night. He knows that.
yeah. But
Yeah.
if you make sure that he only charges when the lowest rates are available, it helps.
After midnight.
No, he does that. He does that already. And I'm still saying it's surprising to me.
I think, Darby, another possibility is that we've been staying home for the last year. And if you've been noticing this rise over the last year, it might not just be EV, but lights during the day, you know, just more electric usage since we're not out and about as much. That's
Well, I'm sure that is a factor, but no, anyway, I'm just curious. Thank you.
Okay.
Oh, this one is on how the EPA ranks EVs. There's a note down here that says, let's see, they've got a, well, they have rated ranges for these cars, and this is hard to read, but unfortunately, oh, here it is. The rated range is like, say, this Tesla Model 3 Standard Range Plus, 263 miles, I think it says. But the way that they calculate that is based on 45% highway and 55% city driving. And unfortunately, you get much more efficiency in city driving. Like in this case, it's 150 mpge city and 133 highway. So if you want to use that range number as far as driving to some place to see how often you have to stop for recharging, it's not a very good way to calculate it because they're overestimating the efficiency you'll see, or the MPGE, the miles per gallon equivalent on the highway. You're not going to get the number that they give you on the highway. So it's almost always the case that when you're driving at 70 or 75 on the freeway, that you won't get the range that the EPA tells you. And this MPGE is not a very meaningful number, because what they're saying is if you take all the energy that's available in a gallon of gasoline and you convert it perfectly to electricity, which is always impossible to do from the laws of thermodynamics, you would get, this is what you'd get. But at best, you can only do about 62% of that in a very efficient power plant if it's burning fuel. But it gives you a comparison number between cars. And that's useful as a figure of merit, I guess. So how far can you go on a charge? And it turns out it depends on temperature. If it's cold out, the battery is less efficient. You get more rolling resistance. Your lubricants are thicker and stiffer and offer more resistance. And you often run the cabin heater, which unfortunately adds a lot of burden to the battery. They've improved that in the most recent Teslas by, instead of using resistance heating, which is just like an electric heater, they put in heat pumps, which will allow more efficient cabin heating. The speed also affects your range, and if I drive from here in Aptos out to Corralitos, which is about 8 miles each way, I will get about almost 5 miles per kilowatt hour. But when I'm on the freeway going 70 or more, I get less than 4 miles per kilowatt hour. So it's affected by both of those things. This is a chart of some of the longest range cars that are available. In case the Model S Long Range Plus is rated at about 390 miles on a charge. The X Long Range is 350 or so. And then last year's long range Model 3 was 322, and I think they're claiming now that that's 352, and that the Model Y long range is about 326. You can't really use those numbers when you're going down the freeway to get from one place to another. Also, independent testers like Edmunds, the company that rates cars in various ways and gives you price estimates, tested a number of the most efficient electric cars, and they come up with numbers that are really quite different in some cases from what the EPA does. And so it pays to be a little bit skeptical about the EPA rated ranges. This, okay, yeah, I've got the reference there. This is taken from user data. This is the real world range versus temperature, that ambient temperature outside. And it depends, it's an average of a lot of people. So some people like me don't use their cabin heater on a cold day. We just use the seat heaters. So we could get higher efficiency. But you get a really substantial drop, and then there's a sweet spot around 70, 75 degrees where you get the greatest range and the greatest efficiency in operating these things. So, your gasoline-powered cars also have a curve like this, but I don't think it's as extreme. But certainly, you get a lower fuel economy on really cold days. And then the effect on speed, on efficiency. This is the vertical axis is in watt hours per mile, and then the speed in miles per hour. Again, this is taken from user data. A Better Route Planner is a website you can go to, and they have a blog, and they have a user community that allows the organization to share some of their data. And so they've taken that data and collected it and plotted it here for different models. And you see that there's a definite minimum energy consumption versus speed. It also it doesn't take into account that you may be operating the air conditioner or the heater at the same time, and if you are, there's a big disadvantage to going slowly, because then all of your energy, if you're going very slowly, is going into your heater or your air conditioner. So it's all amalgamated, and a lot of those other effects are lost. But it gives you an impression. It shows that you get a really different efficiency versus speed. Charging, most of the charging can be done at home, unless you're driving long distances all the time. And the 240 volt 50 amp circuit will give you, like in Jenna's car, about 30 miles in an hour. So in 8 hours, you can gain the full capacity of the battery. The 120 volt 15 amp circuit provides about, say 3 to 6. For a very inefficient vehicle, it's about 3, and for the most efficient electric vehicles, it's about 6. So overnight, 12 hours, say from 9 at night to 9 in the morning, I can gain 60 miles on a charge on a plain 120 volt 2-prong plug-in. Level 2 chargers are pretty much like the 240 volt home chargers. They're about 6.6 kilowatts. And that's the kind of thing you get with charge point. There are 4 charge point chargers down at Severino's at the Seacliff Inn, and there are lots of them in parking garages and things like that. So you can gain about 6 miles an hour that you're charging on those. DC fast chargers are much faster. There are Tesla Superchargers. There are others with a CHAdeMO or CCS connectors, and the networks that I have read about are Blink, ChargePoint, Electrify America, which is being built by Volkswagen, EVgo, Tesla, and Volta. And I've heard of Electrify America and EVgo from people who charge. And ChargePoint I use myself. And the Tesla Superchargers, which are proprietary and not available to other cars generally.
Why is there a range on charging from 15 to 30? Why would it be in the 240 volt?
Well, it depends on the car. There's some cars that are large, electric SUVs, for instance, that don't achieve anywhere near the efficiency of some of the best ones.
So like a Tesla C would get towards the higher end per hour on 240?
Well, the Tesla Model 3, would be on the higher end.
Okay.
And the Model X, for instance, performance would get a lot less. Unfortunately, we don't have standardized or a consistent standard. There are several different types of connectors. J1772 is what ChargePoint uses, and I think most electric cars that are sold in the U.S. will come with an adapter for that, even if it doesn't. So basically, you've got a little short plug adapter that goes onto the end of your charge port on your car, and then 1772 goes in and fits it. Don't need to talk too much about that. The maximum charge rates on the fast chargers all are sort of at the beginning when the battery is kind of empty and hasn't started getting too hot from charging. And so if you've got a version 3 Tesla supercharger, it'll start out quite low and then rapidly go up to its maximum charging rate. And then as you approach 100% charge, it diminishes slowly as you continue charging. So you don't get the 250 kilowatts for the whole time that you're charging. And so it's just, I thought I'd put this in so you could see that it's, you're not going to get, 1,000 miles an hour of charging through the whole charging session. So oftentimes it's better to stop if you're in a hurry, to stop briefly, 5 or 10, 10 minutes, 20 minutes of charging at multiple charging stations rather than a whole long session at one on a long trip.
On that front, Mark, is there still a trade-off between charging speed and battery longevity? I mean, have they calculated so you don't damage your battery?
Yeah, well, the reason why it declines like that is because it's likely to damage the battery if you stay at a high rate as the state of charge goes up, and it's programmed into the controller in the car. It reflects the state of charge and ramps down the rate. It also will reduce the rate if the temperature is too high. So and it operates the cooling while you're charging. So
with that charging profile, you would expect very negligible damage to the battery?
Supercharging does reduce the life of the battery, but the length of time the average person keeps the car, it may not be important. If you can go, say, 450,000 miles before you get to 80% of your original capacity, it takes a lot of people a very long time to get to, say, 150,000 miles on a car. So a lot of people will never notice the difference. They had a company, Tesla, that did Tesla cars using a shuttle service from LA to Las Vegas. And they operated those cars daily and supercharged them all the time from nearly empty to nearly full. They still get 190,000 miles on the battery. So yes, it reduces the higher rates of charging do reduce the life of the battery, but the life of the battery is quite long and it may be acceptable to you. You don't want to do it all the time if you don't need to.
Thanks.
This is the level 2 chargers. It's not new. It's probably a couple of years old. So I'm sure there are more, but these are the kind like the ChargePoint 6.6 kilowatt chargers, and it shows the distribution of the stations in the U.S. These are the non-Tesla fast chargers, the CCS and CHAdeMO, like the EVgo and Electrify America stations. And it's also a couple of years old, I think. So they're building out these networks pretty rapidly so that this is sparser than what's available. This is kind of an
I have a question on the previous chart. Has each individual state now indicated, as they do on their interstate or intrastate. When there's gas, to buy gas, is there such a, are they indicating that nowadays? I haven't seen it. That
I don't think they put up signs where
Yeah.
where there are chargers.
yeah,
But
that would,
most of the cars
Ah.
have in their navigation systems
okay,
will tell you where the nearest charger is, and
Okay.
and in some cases they'll tell you, like the updated navigation system in the Tesla will tell you where the nearest charger is, how many chargers are there, and how many of them are open and available. Um,
okay, thank you.
on your display in the car. So this is a pretty up-to-date map of North America Tesla supercharger station.
Huh.
You can't drive to Cabo because the last place to charge in Baja is Ensenada, and there's some pretty sparse links getting down to Mexico City, but it's possible.
Looks a little sparse in the Midwest too. I mean, or I shouldn't say Midwest.
Yeah,
More than
well, a
Midwest.
lot of the Western Plains, basically, they're along the freeways.
Mm.
There are other things called destination chargers, which I haven't shown here, that allow you to charge at a lower rate when you're staying over at a hotel, and also you can see those on the display in the car. If you set up your navigation to go to some destination and you'll need to charge along the way, it will tell you the optimum station to go to and navigate you to those stations. So, and Tesla's has a reputation of being more reliable and more available than the other networks. And I think part of that is that they have an incentive to make the charging
Absolutely.
network work because they want to sell cars. And if you get a lot of stories out about inconvenience and horror stories about trying to go somewhere and not being able to charge your car, it diminishes demand quite a bit. So they have a bigger incentive than some of the other operators on making sure that these things work. This shows some of the nearby superchargers. We got one in Watsonville, one in Santa Cruz, one in Moss Landing, Gilroy, Hollister over by Casa de Pucha, Santanella. There's a bunch over on 395 in the Owens Valley, and there's a bunch along the 99 and 5. So you can go just about anywhere in California using superchargers to stay charged up. And then they've got a pretty extensive network in Europe, and there are also there's a higher density of other non-Tesla chargers, fast chargers in Europe as well. But they're a lot of fun. So. And then in Asia and the Pacific, there's quite a network. They're building a big network in China and Japan. Not all built out yet, but since they're building hundreds of thousands of Teslas a year in China now, they have a pretty substantial market there too.
What do you think of GM's decision to go all electric by, forget what year it is, in the near future though?
I think it's a good idea, or at least a good aspiration. I think that the technology is going to be there. Every year, the range of these cars is getting longer at the same time as they're getting cheaper. And I think that we have, other people may disagree, but I think we have a real climate emergency, a serious crisis that we are behind the curve on. And that it's urgent that we stop burning gasoline and diesel fuel to propel our cars. So yeah, I think, I think that that they see the same things that I've been showing. The trends in the battery costs are definitely steeply downhill in terms of cost, and the internal combustion engine cars in the next few years are going to become uncompetitive.
Aren't we going to need more electricity to power all these cars?
Yes, we will. But a lot of the time, nighttime, the grid operates well below its current capacity. And we have time to build that capacity. And we have time to build that as renewable capacity.
Mark, recently I got just a small hybrid, and you have a choice of a standard one or a premium with lots of bells and whistles. Obviously, when you were telling about the Tesla's planning your trip across the country, that sounded wonderful, but that sure is a bell and whistle. In cars nowadays, anything more complex, the more complex it is with the cute features, the more it's wonderful while they still last, but it costs a lot more than what we used to think of as ordinary maintenance of a car. I guess my question is, can you compare the bells and whistle factor on electric cars to bells and whistle factors on the present cars? Let's say after their initial honeymoon period of 3 or 4 years.
Well, there are a lot of things to break on a modern car, but even a Prius now has radar. The newest ones, they have radar. They have proximity sensors all over the car. I'm not sure if they have cameras. Yeah, there are a lot of things that it could possibly break, and I haven't heard about really high costs and people having a lot of failures. Like the Tesla Model 3 has 8 cameras, it has 12 proximity sensors, it has forward-looking radar, all that stuff that it uses to drive itself. And it certainly potentially has a lot of potential could break down and cost you a lot to fix. I haven't heard about that happening, but they're not that old. So
I'd like to make a comment about the bells and whistles. One of the really neat things about Tesla is you buy a car and it has, let's say 15 features that you really like. 2 years later, you'll have an additional 10 or 15 features that no bells or whistles are associated with. It's all software. Yeah. It's remarkable how much improvement they've made in ease of driving and visibility and navigation and so on, just with software changes.
Again, they've added 5% of the power, and they've added to the range of existing cars by improving the software over the years. So it's pretty funny.
And my question, I have a question out to the audience, those who do have the Teslas or electric cars. Have you found that manufacturers have finally gone to modular replacement of parts like these bells and whistles, rather than having to tear the whole car apart in terms of replacing those features? I guess what I'm saying is, has the repair feature of the new cars become more efficient?
I think that a lot of the times the things you have to replace are more expensive than they used to be. In general, in cars.
But usually your repair expense has to do with labor hours, and the part itself is more expensive. But the replacement part, for instance, on a car, if you're going to do replacement of electronic on a regular car for electronics of the panel, front panel, whole front panel most of the time has to be taken apart to replace an electronic piece. So,
Yeah.
and that's labor costs. So anyway.
I can answer that question
Oh,
with data about 20 years old.
oh,
And that's that as even 20 years ago, the number one cause of failure in combustion vehicles was electronics. And this was like electronic ignition and the first couple computers. Now, even a combustion engine vehicle has miles of wire, multiple computers. And so there's probably almost no difference between the electronic complexity. In fact, in a lot of ways, because you don't have to monitor ignition, you don't have to adjust, the leanness of fuel and stuff like that. It's probably more straightforward in an electric vehicle, in terms of the computing and things like that. So I don't think that combustion engines have any comparison. What has happened as a trend is that things are modular, but they're big and expensive modules. And so I think you will find with either type of vehicle that the manufacturer, rather than have you mess at a level, is going to have an $800 like a BMW. If you mess up the radio, that's $1,000. If you change the cell phone, that's $1,000. So I think that we will probably have less labor hours, less smart people required,
right.
more self-diagnostics, but still very expensive modules to swap in and out.
Well, I don't mind that. I'm just saying that because I do have a member of the family, he's a mechanic. So I have a little experience in what he charges or what he has to charge, to cover his costs. And it turns out that now, many times, even in the newer cars that have a lot of electronics, to get to those electronics is, very inconvenient, I should say.
Yeah. I think they've improved the reliability of a lot of stuff in cars.
Right.
I've had a couple of Priuses before I bought Tesla. The 2005 I drove 222,000 miles. Had one unscheduled repair or one unscheduled item was $500 coolant valve that had to be replaced in the whole life of the car, and I traded it in and got, it was still running great. And the second one I ran about 140,000 miles and never had to do anything to it except routine maintenance. So there are modern cars that are extremely reliable and have very low maintenance costs.
Okay.
Especially Toyotas.
Yeah, and a BMW I had before that cost me a fortune. So
I'd also say, Constantine, that a lot of that is just bad design. And part of the learning curve is learning how to design cars for maintainability, get the bugs out. Early in my career at Ford, we used to joke about the dipstick engineer, because the automatic transmission dipstick guy was the very last guy to get to design something. And in some cases, they had as much as a 14-foot dipstick to get to the office. So you learn, if you stick with a basic design and get to refine it year after year after year, stuff gets a lot better.
Okay. All right. Never mind.
I've got a couple more slides. I wanted to show solar power price trends. Solar power has gotten to be cheaper in some places to put in new than to keep operating old thermal power plants. And that trend, I think, is still continuing. So if you take a gas burning plant or especially a coal burning plant, you can build new solar in some places cheaper than you can continue to operate power plants that have been there for decades. And so even without incentives or a concerted societal push toward adapting to renewables are becoming more practical in a purely economic sense. Wind energy, the same. it looks like sometime around the year 2000, it hit a cost point where it started to take off because the cost was low enough to displace other types of energy. And so the cumulative wind capacity, that butterscotch colored curve that's going up, is growing very rapidly as the cost of wind energy continues to go down. So operating electric cars is going to continue to get cheaper. And that's my last slide.
Thank you.
Mark?
Mhm.
Mark, could we return us the picture?
Oh,
Okay, this is Rusty. Barry won't let me up here.
who's everybody? Okay.
Okay, anyway, I'm a little concerned about all the stuff that we're accumulating. Okay, like, as I understand it, solar panels and windmills both, what, I think they last about 20 years. That could be wrong, and then they have to be replaced. What happens to them? And batteries, do we have some way to what extent are the batteries recyclable?
Well, one of the major players within Tesla has gone off to start a company to develop a complete system for recycling lithium-ion batteries. I forget what his name is, but he was one of the big players in the executive suite at Tesla, and he has gone off to start a venture to recycle all the materials in lithium-ion batteries.
Yeah, I must say that that I think his facility is in England or Britain, and actually it's on the market. You know, stocks are on the market for the company. It's not new anymore. So, yes, that's true.
Yeah, you're really recycling them for the elements in them, so that it'll take some energy, but you can reuse almost all that material.
That was a terrific presentation, Mark. Thank you for that. I've got one comment and a question. To Rusty's point, one of the other trends we've got is this hiring out of vehicles, so that if a vehicle can basically be used to exhaustion and shared between people, we make a whole lot better use of what we've going on. So I mean, that's a positive trend. The question I had for you, Mark, is I wonder if there's a cultural aspect to this, because we almost seem to be divided as a nation between two cultures, one of which is black smoke and 500 horsepower, and NASCAR is what real men do and what real women, want to accompany, and the other and the other is that, I kind of intuitively knew with this, but on average, I mean, there's a lot of torque with electric motors. It's like a half a horsepower motor running these things, 300 watt hours per mile or something like that. And I'm just wondering if you had any comments as you were doing research of how these cultures are going to sort themselves out.
Well, there are some real rowdy people. There are people who buy a diesel truck and get an aftermarket chip that allows them to burn richer than is allowed for emission standards, and they have this practice called coal rolling, where when you put the accelerator to the floor in this diesel truck that's been modified, this huge plume of black smoke comes out of the exhaust, and they like to do that to people driving Priuses and Teslas and things to just to be in your face. I don't know how it's going to resolve, but the guys with the hot rods and stuff are finding out that if they pull up to a stoplight and roar their engines next to a Tesla, they get left in the dust. It's there's a little bit of giving it back to them, I guess. I don't know how this cultural thing is going to resolve. It's sort of like the the anti-vaxxers and the, you know, the owning the libs and all this stuff, the people are doing things, object to the idea that you should try to, you know, that you believe in global warming or any of this stuff. I don't know what you do about that. There's a part of the culture that wants to believe what they want to believe and want to do what they want to do, and I don't know what they're going to do.
Let me add to that. There's some in Europe, I understand there's an Formula One or something racing circuit going on. So some people are moving forward and others are not.
Well, the coal rolling mention may be a good segue to next month's talk, which Rusty and Barry, I understand, is still going to be on EPA, and I'm just wondering if people. So it's kind of what's the history of environmental regulation in the U.S. and things like that. Rusty, I believe this is a friend of yours. Can you sort of prime us of kind of questions, feedback, things that Chuck might want?
No, I can't.
All right, Rusty's being shy about it. Let's see. So this is a high school classmate of Rusty's who went on to Yale Law School and then worked for the Environmental Protection Agency for his whole career. He is the founder and the president of the EPA Alumni Association currently, and rose to the point of being director of toxic substances at the FBI. So he's
FBI
at the EPA. So he is going to talk about basically his experience at the EPA. I mean, part of it, the regulatory, part of it, the political. We just thought it would be a great chance to really see the inside story of somebody who really knows how one of our most important agency has run in the past. And he certainly has opinions on its recent history.
And a lightning rod for all these cultural issues.
Yeah.
Yeah. Okay. Well, that's coming up. So if people have questions and thoughts, maybe send them to me, and we'll get them back to Chuck and go from there.
Right. And we should say he lives in Washington, D.C., and the talk will be live from Washington, D.C.
That's great. Well, Mark, thank you very much. That was very informative, and we'll go for, yeah, exactly. So
if we've got any more questions, I'm open to answering them offline or email or whatever.
Do you know anything about batteries for solar? Can I send you a question after on that, or would that just be so far out of?
No, sure. I know a little bit about it.
All right, thanks. That'll be helpful. Thanks.
All right. Thank you all.
All right.
Happy Easter.
Well, maybe I'll just keep this open so if people have questions for Mark, we can ask.
Okay.
I do it because I have a question.
Thanks, Mark.
Okay.
Regenerative braking, how does it slow the car down?
Well, it essentially it puts a magnetic drag on the rotating parts of the electric motor. You know, if you in both the Prius and in the Tesla, you have a rotor with permanent magnets in it, and it's surrounded by a bunch of coils. If you have that magnet moving by those coils, it induces electrical voltage in those coils. So if you allow the current to flow out, it exerts a braking torque. It operates as a generator, and so that in the motor, it's actually a magnetic force that's impeding the rotation of the rotor.
You can think of it, Barry, as when it's acting as a motor, it's going in one direction, and when it's acting as a brake, it's generating with the same kind of force, more or less, in the other direction.
Okay.
And what they have to do, of course, is to, in order to operate as a motor, you have to supply a higher voltage than this natural, what they call back EMF, that's generated by the magnets moving by the coils. That allows you to operate as a motor. When you're taking energy out, you actually have to be able to take it out at a lower voltage than that because you have resistance and things in the motor. So you have to step it up to the battery voltage. And they use what they call a DC to DC converter that that takes that lower voltage and steps it up to the higher voltage that allows it to charge the battery with.
But ultimately, it puts a pretty strong physical force on a piece of metal somewhere.
Yeah, that's right. And yeah, that spinning piece of metal, it exerts a force on. You can do a lot more of the regenerative braking with a large motor than you can with a small motor. So you get, you can take 300 horsepower of braking energy and put it into the battery of the Tesla, but the motor in the Prius is much smaller, so you can't get that as large an effect. But it's still helpful a lot in a Prius.
Barry, you might be interested. I think I've told the story before, but in the conjunction between electric vehicles and capitalism, your recession, Sandy Munro is this very famous benchmarking guy. He's got a thing that basically did teardowns of automotive vehicles and other products as well to determine what was really good about it so you could get lessons learned. And he was hired a couple of years ago to do a teardown of the Tesla. And he said, he came in very skeptical, but he said, this is really great battery tech. They do a bunch of things really well. And he got sued for saying that because the people who hired him this time didn't want to make better electric vehicles. They wanted to short the company. And so we are now at the stage where the people running our economy are investing in research projects, not to make better products, but to skim some money off the top on the stock price. So that I don't. Did you ever touch base with Sandy, Mark?
I haven't touched base with him. I've read some articles about his teardowns and his remarks on that stuff. It's apparently is very impressed with the electric motors that Tesla has designed.
And the batteries, yeah. He didn't like how
the
they
batteries.
Were,
There's another thing in there too, which is the inverter, which I think is more advanced in the Tesla than it is in a lot of the other cars.
What was the name of the fellow who wrote that report?
Sandy Munro, M-U-N-R-O. So I've known Sandy probably for about 30 or 40 years, and he does bench downing. So we've done like work for clients on Caterpillar and Deere and golf course, but a whole bunch of automotive companies. And so he will literally take a car apart and see and infer how it was assembled, how it was produced, and learn what the best practices are. And so his deal is design for manufacturing and assembly. How do you basically go down that learning curve that Mark was talking about? So if instead of like taking 10 hits on a die to form a hood, how do you do it like Toyota does in 3 and things like that? So M-U-N-R-O, Sandy Munro. Yeah, I'm sure you'll find YouTubes with him. He's an older guy now, but you'll see him being interviewed, and you'll see the whole debacle with Tesla and so on.
Yeah, that sounds interesting. Thanks.
Yeah, there's a lot of stuff about him on like Electrek and clean energy websites and stuff like that. A lot of videos they post. So it's a technology that's still developing and still getting better. So.
Okay, I got one more. So if a lot of the cost is in the battery, would it be feasible to have a sort of a town car, a little town car, in which you just simply, instead of 1,200-pound battery, put a 200-pound battery in it?
Sure.
And
Yeah, and they do that.
Electric car, if you aren't going to drive more than 70 miles in a couple of days. Are they out there? Anything like that?
That exists, Barry. You just have to move to Florida and join a retirement community and drive a golf court.
No, a lot of it, like the BMW i3, I think has less than 200 miles of range, maybe 140 or 150, something like that. And they're available a couple of years old for about $17,000 in some cases. The price of a lot of used electric cars, except for Teslas, drops really rapidly. And so like I said, this car, which was over $40,000 or something like $40,000, this BMW i3, which is small, and it has a relatively small range and a small battery, you can buy one used for under $20,000 and still in really good shape. So if you're really interested in having a city car that you never drive very far, there are those out there, and they're available cheap used. Jenna's car is a smaller range car. It has a battery that's about 2/3 the size of the long range, and so it's several hundred pounds lighter and about $8,000 cheaper than a long range. So that's an approach that's, and some of the Nissan Leafs, if you don't drive them at highway speeds to heat up the battery, you can get good range out of those, and they're much cheaper, especially used. But the early ones didn't even have 100 miles range. So, but that would be great for a town car, a city car.
Maybe another question, Mark. What's your domain at Pacific Scientific now? Are you in the blow stuff up part, or what kind of work are you doing?
Well, almost all of what I do is in the basically ballistic missile interceptors, and really what we do is explosive devices and initiation systems that are used for operating things like rocket motor ignition and stage separation, cutting lines, and blowing off covers and things like that. You have a little explosive cartridge or a pressure cartridge that's operated. Most of the work I do is with laser initiation of using fiber optics and diode lasers, and some of it's electrical, and my role is mostly mechanical and optical, and so. But we have a couple of major missile systems that use the laser initiation for doing these various operations in operating these missiles.
Is the advantage of that speed, or what's the?
For the laser, it's because it is absolutely impervious to electromagnetic radiation and static. And that's sort of inadvertent initiation or induced currents and things like that can accidentally set off electrically fired initiators.
So all the EMF defense systems aren't going to work against this. Yeah, cool.
Right.
Thank you very much.
Thank you.
Okay.
Thank you, Mark.
All right. Good.
Thank you, Mark.
So in the end, you got the whole crew, Mark. I think we had the usual crowd show up for
Okay.
Easter Sunday. All right.
Happy Easter.
Happy Easter.
Thanks, Mark.
Really
Happy
good.
Easter.